We're living through an incredible time, a full-on medical revolution, really. At the heart of it is artificial intelligence, which is quickly becoming one of the most powerful tools a doctor can have. But it turns out this revolutionary new tool has a surprising and sometimes pretty dangerous blind spot. We're talking about AI that can sift through millions of medical records in the blink of an eye. These models are learning to read an X-ray with superhuman precision, spot the faintest little flutter on an EKG, and see the very first signs of disease that a human eye might just miss. It's really like giving every single doctor an unbelievably powerful co-pilot. Because here's the real mystery we're diving into today. These incredibly sophisticated AI tools, the ones designed to save lives, often just fail. And sometimes fail dangerously the second they're used on kids. So the big question is, why? To solve this mystery, we had to start with the single most fundamental rule in all of pediatrics. It's a concept that, once you get it, explains everything else that follows. Just think about it for a second. A person goes through the most radical biological transformation of their entire life in those first 18 years. You go from a tiny, helpless newborn to an infant, to a toddler, to a child, and then an adolescent. And each of those isn't just a different label. It's a completely different biological reality. And what's so fascinating is just how messy this growth is. It's not linear at all. If you follow that blue line, that's the brain. It just explodes in size in the first few years. And it's pretty much adult size by the time you're 6. But then look at the green line, the reproductive system. It just hangs out almost dormant for more than a decade before it suddenly takes off at puberty. Nothing grows in a neat, predictable line. And that right there, that's our crucial clue. An adult body is, biologically speaking, relatively stable. A kid's body, on the other hand, is like a construction site where different crews are working on different projects at completely different speeds. And this non-linear chaos is exactly what confuses an AI that was trained on stable, predictable adult data. It all comes down to this one simple phrase. You can't just take adult medicine and shrink it down for a child. Their whole physiology is fundamentally different, and that single difference is the root of this entire problem. Okay, so we've got the first piece of our puzzle. A child's body is in constant flux. So now, let's connect that biological chaos to the one thing an AI model actually understands: data. This brings us to this key idea called data heterogeneity. I know, it sounds super technical, but the concept is actually really simple. Imagine you train an AI to be the world's greatest expert on apples. You show it a million pictures of apples. It knows apples inside and out. Then you show it a fruit salad and say, okay, identify everything in there. The AI, knowing only apples, would be totally lost looking at oranges and grapes and melon. That fruit salad, that's what pediatric data looks like to an AI trained only on adults. This chart illustrates the problem perfectly. Take a look. For a baby under 1 year old, a normal heart rate can be as high as 160 beats per minute. For them, that's totally healthy. But if you or I or even a teenager had a resting heart rate of 160, well, that would set off some major alarm bells. The very definition of normal changes completely depending on your age. And it's not just heart rate. We're talking about everything: the size of their organs, the density of their bones, their breathing patterns, the way their immune system responds to an infection, their normal lab values. Every single data point is a moving target all the way through childhood. All right, so now that we get this fundamental data mismatch, let's open up a couple of real-world case files where this problem goes from just being theoretical to being genuinely critical. So our first case involves an AI model that was built to spot heart rhythm moments. So here's what happens. The AI looks at the data from a 2-year-old and sees a heart rate of 120 beats per minute. Now, for a toddler who's been running around, that's completely normal. But the AI, which only learned from adult data, has been taught that anything over 100 is tachycardia, a dangerously fast heart rhythm. So it throws up a big red flag, a false alarm that could lead to needless tests, unnecessary medication, and a whole lot of panic for everyone involved. Our second case moves from heartbeats over to bones, and we're looking at medical imaging this time. Okay, this one is genuinely wild. A child's bones have these things called growth plates. They're basically soft areas of cartilage at the ends of bones where all the growth actually happens. But to an AI that has only ever studied fully formed adult skeletons, these totally normal, healthy growth plates look exactly like a fracture. The result? The AI flags a healthy, growing kid as having a broken bone. So we've seen the problem and we've seen the consequences. The big question now is, what's the solution? How do we actually build an AI that can handle the incredible complexity of a growing child?
Well, it turns out researchers are focused on two main strategies, and a good way to think about it is with a recipe book analogy. The first approach is what they call age-stratified models. This is like creating completely separate recipe books, one for babies, one for toddlers, one for teens. Each one is a specialist. The second approach, age-conditioned models, is more like having one giant master recipe book, but with special instructions inside that say, okay, if you're cooking for a 2-year-old, use half the salt. If you're cooking for a teenager, you can add more spice. It's a single, smarter model that adjusts its recipe based on the patient's age.
And we know this actually works in the real world. This table shows what happened with a model built to predict sepsis. When they used a standard one-size-fits-all AI that lumped all the kids together, the accuracy was pretty low. But look what happens when they took that age-stratified approach, splitting the kids into 4 distinct age groups. The performance shot way up because each model became an expert in its specific little group.
So really, the key takeaway here is that you can't just take an AI built for adults, test it on a few kids, and call a day. It doesn't work. You have to build these models for children from the ground up. That means designing it for their unique biology, training it on their specific data, and, this is critical, validating that it works using data from that very same age group. If there's one thing to remember from all of this, it's this sentence right here. It perfectly solves our mystery. Age shapes biology. That biology shapes the data, and that unique data is what we must use to build AI models that are safe and effective for our kids. It's a chain of logic that we simply cannot afford to break. And all of this leaves us with one final crucial question. What we've seen here with Pediatrics is actually a really powerful warning. As we race to build this amazing future of medicine, how do we make absolutely sure we don't leave anyone behind? How do we build an AI that is designed from the very first line of code to care for every single patient, no matter how old they are?